Hi, today's tutorial will be focused on a one-class segmentation. So what does it mean? As you can see, we will learn how to detect floats. Float will be our one class. And after the training and building the model, we can grab and segment the float out of a test image. So let's start. Okay, let's start first of all with the installation process. As you can see, we will create a new Conda environment. Let's name it Yolo V8, and we will install Python 3.8. Then we will activate this new environment. Next, we need to figure out what is our CUDA version. So in order to do that, we will run this command. And in my environment, it is 11.8. Then you have to go to the PyTorch website and look for the relevant installation for your CUDA installation. And mine is 11.8, and there are several PyTorch that support 11.8. I chose 2.1.1, so this is the command in order to install the PyTorch in my environment. And after that, we will install Yolo V8. This is the command in order to install Yolo V8.1. Next, after installing the Yolo 8.1, we have to reinstall the OpenCV Python library list. So we have to uninstall the OpenCV Python headless, the one that doesn't have all the visual objects and functions. So we will uninstall OpenCV headless. We will uninstall the OpenCV Python, the full Python library, and then we will reinstall it once again. So this is the process in order to create the relevant environment to run Yolo V8. And now we are ready to start the segmentation process. Okay, in the next step, we will download our dataset. So basically, this is the link for the dataset. As you can see, it's a float area segmentation. So it's based on images and masks. I will leave a link for this dataset here in the code. So you should download the images and watch some of the images. I already downloaded the images. As you can see, there are two folders. One is named image and contained all the images. As you can see here, there is one image. Let's watch the image 1 second. Okay, so this is the first image, the second image, third image, fourth image. So you can see this is the float area. Let's see another image. You can see this is the float area of the image. And if we go to the second folder named mask, you can see that there are masks of the float. The white area is the float, and the rest of the areas is not a float. It can be houses, it can be mainland, but basically the white are the float areas. Let's, for example, see image number 8. Let's make it smaller. And let's go for image and open image number 8. Okay, so now we can put one next to each other. As you can see, this is the float area and here is the float area. So this is the dataset, and now we are going to learn how to convert this dataset, since basically this is a color image and this is a black and white image. That means that all the white areas have a white color and the rest of the area has black color. But since we are going to use Yolo V8, we need to convert this image to a label, and the label should be in a Yolo format. So let's continue to the next phase. Okay, so the next process that we name it step number 1 is converting those images to a YOLO format. What does it mean? So this is our input dir, and this input directory is referred to all the masks, and basically we are going to create a label directory, and this label directory will have txt files, and each txt files will be based on the YOLO format. So what is a YOLO format? If you go to this example file, as you can see in this file, we have 4 values to each point. And if, for example, we go to the first character, that means 0, and this 0 is meant for a specific class. For example, this specific class is in x point 0.5 and in y point 0.4, and this is the width and the height ratio from the total image. So this 0 class can be a person, can be a car, can be a dog, and also can be a binary file, like 0 can meant to be all the white area and white points, and 1 can be black points. So this is a YOLO format. And if we go back to our code, the purpose of the code is convert all the binary mask images, which are basically black and white images, and the white area represent the region affected by flood. So these masks are typically in a format when the white presents the flood areas and the black parts present everything else, like houses and mainland. And the YOLO format, as I mentioned earlier, represent objects by specifying their bounding boxes or shapes. So let's explain more about the conversion process. First, we will read the mask. So we will run a loop through all the images in the mask directory. Then we will do a threshold. What do we mean by that? We will convert the mask into a purely black and white images, where white pixels represents the flood affected area. Next, we will use the find contour function. So this identifies the boundaries of the white area, and we will find the outline of the flood regions. Next, we will convert these contours to a polygon. So polygon basically is it's a bunch of points that are dotted one to each other. Each content represents a flood region, and it's converted into a polygon. It's like a shape of multiply straight sides. Next, we will write each of the masks into a txt file, and this will be the YOLO format. And finally, the script saves the coordinate of these polygons into a text file. Each line in the text file represents a polygon. So basically what we are doing, we are converting or changing the representation of the flood areas from a binary mask to a format that is more suitable for training and Yolo V8 machine learning model. So let's run the code and let's see the result. Let's go to the folder, and as you can see, the original information was images. Basically it's named image folder and mask folder, and now we created a new folder named labels, and for each of those images there is a txt file. And if we'll open this file, as you can see, there is a polygon for each of those data points. Please notice that this is the object and it represents, all the data is represent until here, and this is another area, another float area, and these are all the points until here. Okay, the next step of the data preparation is split the data. So if we go back to our folder, we have images and we have labels. Now we have to create two folders, one for the train and one for the validation, and under each of these folders we have to create another two folders. One will be images and the next one will be the labels. So basically we are creating four folders, two for the train and two for the validation. And it's very important to keep the names. One should be images with S and one should be labels. So this is the code for that. It will split the data and create these images and labels. And what we are going to do, we will split the data with 80% for train and 20% for the validation. So this is the source folder, and we created train, validation, and split it by 80%. So this is the code for that. Of course, I will leave a link in the video description for this code as well. Let's run it. Let's go back to our folder and it's finished. So now, as you can see, we have train and we have validation. If you go to the train, there are images folders. As you can see, these are 80% of the images and the correspondent labels. For example, you can see that we have image number 0. Image number 1 is not here, probably it's on the validation. Image number 2, 3, 4, 7, 9. All these are the correspondent YOLO format labels for these images. And the same for the validation. As you can see, there are images and labels. So after preparing the data, creating the relevant folders, creating the labels, we are ready for the training part. So let's create a new Python file. We'll call it step number 3. Let's import Yolo out of the Ultralytics framework. Let's create a main function. And first of all, we will load the Yolo model. As you can see, we will load the LSEG, that means the large model based on the segmentation process. If you go to the Yolo V8 website, you can see that all the models are divided to segments. So this is detection and this is segmentation. And out of segmentation, there are 5 models. We will choose this one, which is named 8L. 8L is for large. There is a nano, small, medium, large, and extra large. Let's choose the large. Each model has a better accuracy, but it takes more time to do the training process. Now let's define a project name. Basically, project name is a folder where all the results would be stored, and the experiment part is a subfolder under the project name. Let's define the batch size. I chose 16. It really depends on the hardware, how strong is your GPU card. Next, we'll define our config file. It's part of the Yolo V8 framework. We have to put the relevant path for the train images and the validation images. And next, you can see is how many classes we have in our model. This specific tutorial we are running with a one class. This is the flood class. So basically it's a float or non-float, so we are running only with one class. Don't forget to change the slashes, the direction of the slashes, and now we are ready for the training process. We will send several arguments. First of all, the first argument is the path for our config file, then the number of epochs. So let's run it with the 100 epochs. Next, the project name and the experiment name, both we defined earlier. Experiment, okay. Next, the batch size, in our case, is 16. And next is the device. 0 means GPU. If you are using CPU, you should put CPU. The image size, very important. In the Yolo V8, it's 640. Patience is how many epochs we are going to wait before early stopping. So we will run it with a very high value, 30. And now we are ready for the running part. We will run the main function. I have a syntax error with the name of the, if you saw it, with the name of the model file, and now we start running. As you can see, this is the first epoch. So this is a process. You can look at the segmentation lost value. After the first epoch, it's a 3.0, and if it goes down during the process, we are on the right path. Let's jump to the 7 epoch. As you can see, now the segmentation lost is under 2.9. Now it's at 2.7, so we are still on the right path. So let's jump directly to the last process. As you can see, it stopped after 92 epochs, and the segmentation loss is about 1.6, and this is the path where the results are stored. So let's go to this path and let's open the result PNG. You should look at the training of the segmentation loss. As you can see, it's going down with the right path. Very good. Let's open the validation data. As you can see, in the first batch, it discovered the float. Very good. And this is an example images out of the validation process, and the result seems very good. So now we are ready to test our model with a new and a fresh image. So I downloaded an image of a flood out of Google. You can see this is the image. There are several houses and trees and a lot of flood. So let's create a new Python file. We'll call it step number 4. And the first phase will be import the Yolo object out of the Ultralytics framework. Let's also import NumPy and OpenCV. Now the path for our result to our model, let's go to the weight subfolder and choose the best.pt file. This is the best weights of our training. So don't forget to change the slashes to the right direction. So this is the model path, our model path. Now let's add the path for our test image. Let's also change the direction of the slashes. Great. Now we are loading our test image using the OpenCV library. And let's also extract the height and the width of our image. And now we are creating an instance of our Yolo model, and we are creating this instance with our weights, our pre-trained weights. And now we are running the prediction using the model function, and the results will contain a lot of information. So first of all, let's print the result variable. and let's see what we get out of it. As you can see, there is a lot of information. For example, we discovered that we have nine prediction classes based on floods. This is the original image. This is the shape of the original image, and there are lots of objects inside this result variable. So let's grab some of them. First of all, let's grab the names. The names is basically the classes inside our model. We add these in the config file. So basically we are expecting to see only one named flood. Next, we are creating an empty image. What is an empty image? Basically it's an image with the same size as our original image, but it will be based on 0. 0 means that all the pixels will be black pixels. So basically we are creating a numpy array that all the channels are equals to 0, and this is a black image. Now out of the result we are grabbing or extracting the predicted classes. So this is the command in order to extract those classes, and let's print the result. As you can see, we have the name, which is 0 and flood, and we also have 9 zeros. 9 zeros means that we have 9 masks, and all these masks are the type class 0, which is flood, since we have only one class in our prediction. Now let's iterate and run through those 9 masks. So first of all, let's grab each mask and multiply it by 255 after the process. So basically we are converting the mask to a white color. Then we will get the mask ID, which is 0, and next we would like to print all these 9 objects, and we are expecting to see a 9 object with a 0. That means this is our class for flood, and the name of the class will be flood as well. Let's run it to be more easier to understand. As you can see, object number 0 is detected as 0, which is flood, and also the name of the class, which is flood. Now let's resize it to our image with the same dimensions, and let's also create one final mask that contain all the 9 masks together. So what does it mean again? Each mask has a white area for the mask and the rest is black, and when we are accumulated all the masks together, we are creating one final image that contains all the merged masks at one image. So all the flood area will be white with all the 9 together, and all the rest will be black. Let's say choose a name for that. We will call it output.png. So we will save each of the 9 masks with this name, and also we will save the final mask, which contain all the 9 masks together. So as you can see, this command saves each mask, and now after we finish the for loop, we will save the final mask. Let's call it final mask.png, and also we forgot to add a slash here to each of those masks inside the for loop, so now it's fixed. Great. Now we have to show the results. So let's show our original image, and next to it let's show the final prediction mask image. Since the dimensions are very big, let's reduce the dimensions of both image by 30%. So we are grabbing the width and the height, and we are changed it by the scale %, and then we will use the OpenCV resize function to resize our original image. Okay, now as you can see, we are using the OpenCV function. We are resizing the original image named IMG with our required dimensions that are 30% reduction. And next to the resized image, we will build another variable, another image named resize mask, and we will send to the resize function the final mask image. And now let's display both images, one next to each other, so the resized image and the resized mask. And we will wait for a key pressed. Just change the name of the function. Now it's done. Let's run it. We're expecting to see two images, the original and the mask. Great. As always, I will leave a link to the code in the video description. I hope you enjoyed this tutorial as well. Bye bye.